Welcome to today's class. Last lecture, we talked about hybridizing to make the program run faster without running too much Python code. Today we're going to cover a few other topics to make your code even faster. So the first one is called asynchronous computing. The idea here is that we know that if we're going to run the code on the right hand one by one, every time we need to pay the system overhead. The system overhead, which means to compile to bytecode to run the Python virtual machine. So here we show as the yellow block here, and we pay the system overhead, run the command, and pay the system overhead run other things. So then if we only have a single thread, that is what the single thread, that is what you interact with Python, then we cannot avoid these things. Another design technology here is called asynchronous list, which means we have two threads here. The front end still the Python thread you do interact with. But then we have another backend thread here. The front end do nothing, just compile the code, send the workload to the backend thread to execute. After you send to the backend, you continue to move to the next sentences, which means I pay the overhead for the next sentences and send the workload. And do that by 3-4 times until at the end, we're going to print C. We're going to read the results. But the front end thread finished earlier because I only need to pay the overhead. So I need to wait here until the backend has been done. So the front end wait a little bit until the backend, OK, the C is ready, I'm going to print the results. So what you can see here, we overlapped 3 system overhead here. So 3 blocks at the 3 blocks we are running things at the back end. In this case, if we run a very long Python code and we don't need to get the result immediately, which is usually what we do during a single batch of the neural network training, then we can, no matter how long the program we have, we just send the front thread just send the workload to backend. We don't sacrifice the performance too much. So here, especially in this case, the only overhead we paid is the overhead to dispatch the first sentence. Let's see a real example how it works here. So again, we first define the benchmark function that we will not dive into details. That is, we showed in the last lecture before. Here's the first one. If we put the source code with the bench function scope, we're going to benchmark the runtime. Here, what do we do here? We generate a random matrix with 2,000 by 2,000 and perform the matrix multiplication. We know and sum the result to get a single scalar. We know that both things are sometimes pretty slow because of large matrix multiplication. And at the end, we're going to print the result here. So we're going to benchmark by 2 parts. What you can see here is that the first line, the first line is how to execute the first 2 lines of code. It's actually pretty fast. It's 0.0006 seconds, which means we didn't, once we finish here, if the Python thread runs to here, we didn't run anything, just to patch the workload into backend. Then at the last, we're going to print. In Python, it's pretty easy, just to print a scalar. But actually, we spent 0.17 seconds here to wait, because the front end need to wait the result to be ready. And so the overhead is here. So sometimes you run a program, it runs pretty fast, and you print the result, it's stuck for a while. And actually, it's not because the print is so heavy. It's because we just pushed the workload backend, and it's not finished yet. OK? There are multiple ways to break the asynchronous execution, to wait the result to be ready. So before we should print, we're going to print because you always need to be result ready to print the results. We have multiple ways to do here. One is that you call y is the results. We want to wait the y to be read, which means we're going to wait here until y result is ready. So the time shows here is 0.06 seconds. It's pretty normal stage. And then also we can do multiple things, and we call ND the length space with all the workload, and up to this synthesis push into backend and wait all finished. That is usually how we benchmark some code and show and wait all the result to be ready. Also, if we copy to NumPy, because NumPy doesn't have asynchronous computing, then we need to wait the result ready and copy to NumPy. Similar thing, as a scalar, we also need to wait as well. So you usually don't need to pay too much attention to that unless you're going to benchmark something. At the earlier days, about 3 years ago, somebody wanted to benchmark like MXNet, TensorFlow, a bunch of other framework, and their conclusions like, well, MXNet is like 1,000 times faster than others. Well, it's definitely not true. You know that 95% of great results is due to bugs. You want always debug. But then that's because you only benchmark the time you send to backend. So you need to wait until the results are ready. OK? And so here we show that we run a small workload by 1,000 times. The first one is equal to y equals to x plus 1, and we wait y ready to read. This is because now we do synchronized execution. We pay the overhead, wait the results, and pay the overhead, run the computation, and wait the results. The second one is the normal way how we program, but the only thing we add ND wait all here to benchmark the results. And this is exactly what the slide shows that the first one, we paid more, 0.76 seconds. And for second one, because we don't wait any time, we have at least two threads executing, so we saved at least 0.2 seconds here. Question?
Question. So with asynchronous computing, does it necessarily require additional resources, especially with memories, because you're queuing up feeds?
Yes, you need. We're going to show you in later, but usually don't pay too much to that. We're going to show that, yes, because you're buffering something, you need to put all the things in memory. We're going to show exactly how it happens later. But here you see that, well, to issue 1,000 cores, at least you pay 0.2 seconds. That's a lot for Python. Yes, now we're going to answer the question like how asynchronously going to impact the memory usage. Here we do a simple one to data iterator within a bunch of time here. The only thing here, the key thing here, every time we generate x, it's a random matrix, and a y, and return x and y, and print at any time we want. This is nothing special here. That's a simple data iterator. And we also train MLP. That's nothing special here as well. We define MLP here, 3 dense layers, initialize it, trainers, loss function, and run a single one to warm up. And also we define function that is just to get the memory usage, nothing here. OK, so here's the thing. Here's normally what we do. Every time, every batch, we get x and y, put the autograd, compute the loss, something special here. Usually we compute the mean, and we add a scalar, add into like a sum of loss. So here, we break the batch into one by one. At least until here, we need to wait the forward pass has been done. And then we do the backward pass. We can also move here one line below. That's fine. And what we can do something. So at any batch, we do a synchronization here to break all this asynchronous execution. Usually that's good enough because each batch we have enough workload. We don't need to pay too much attention to that cross multiple batch things. So you can see that the batch 50, the time is 3 seconds, and batch 100, the total time is almost 6 seconds. And the increased memory here is that we benchmark the memory at the beginning, and we benchmark the memory at the end. We didn't increase too much memory for this process. OK? Now let's do another one. We removed S scalar, which means there's nothing. Sam get the memory, read the X and the Y, do an autograd, put into forward and computer loss, do backward, and update. Until here, we wait all. So you can see that, well, there's nothing stop us to push all the things together into backend engine. What do you mean that we're going to push all this intermediate result into backend engine? We're going to read all this data into memory. Well, you can see that during batch 50, this is when we generate the data, it played 0.07 seconds. And at the end, batch 100, 0.14 seconds, which means we generated 100 batches at the earlier time. All this data will be on memory. At the end, we compute that, OK, the increased memory is almost 200 megabytes. That is, all the data input are on memory, and also intermediate result on memory as well. So usually that's not a problem, but one common mistake we have is like, because GPU have limited memory. If you do ImageNet, it's 100 gigabyte data set, you're going to read, and without breaking, you feel like, oh, that's so fast, and all the things are running, and soon you're going to load the data into memory. It's GPU memory, and you're out of memory. That's all. OK, but usually you don't need to pay too much attention to that. OK?